Compositional data, like microbiome profiles or cell type proportions, lives on the hs and simplex. Inference depends only on ratios, not absolute totals. To analyze this, we project data into the hs and tangent space using isometric log-ratio, or ILR, transforms. But standard ILR treats components symmetrically, ignoring domain hierarchies. When trees are known, we use tree-based balances. However, methods like PhILR require binary trees. Real taxonomies are full of polytomous, nodes with multiple children. PhILR forces arbitrary binary resolutions, introducing artificial splits that break canonicity and destabilize feature selection. PolyILR solves this by constructing a canonical orthonormal decomposition for arbitrary tree topologies. The core insight is a local-to-global assembly. At any internal node with k children, PolyILR defines a local contrast subspace of dimension k-1. Crucially, it equips this subspace with a weighted inner product. The inner product of H and H' weighted equals the sum of H sub R times H' sub R divided by N sub R, where N sub R is the number of descendant leaves for child. This weighting compensates for subtree size. When local vectors are spread to the global leaf space via a 1 over N sub R scaling, local orthonormality under the weighted metric guarantees global orthonormality in the Euclidean tangent space. The method uses Helmert contrasts, orthonormalized via weighted Gram-Schmidt, ensuring a deterministic canonical basis given a fixed child ordering. The result? A coordinate system, where every basis vector maps to a specific node in contrast. Experiments on microbiome and single-cell data show PolyILR maintains high feature stability, while PhILR accuracy fluctuates wildly due to binarization noise. It enables multiscale inference, aggregating importance across depth, subtrees, or nodes without double counting, thanks to the orthogonal partitioning of the tangent space. Beyond CoDA, PolyILR reveals a structural link to softmax classifiers. The quotient of logit space under shift invariance is isomorphic to the CLR tangent space. This allows decomposing model gradients into tree-aligned coordinates, localizing learning signals to specific hierarchical branches. PolyILR, geometrically principled, tree-compatible, and ready for multiscale inference.